E2. And sometimes you could say that that's equal to a constant. Right? If linear momentum is conserved, same as what we use for particles, with one exception, you do things based off the mass center. MA VA1 plus MB VB1 is equal to MA VA2 so use one of those equations or both if you can. Okay. Let's do an example. Example is just going to be this guy here. Bullet striking a bar. And stuff's going to happen with it afterwards. The bar is at rest, has a mass of 5 kilograms, struck by a bullet B with a velocity of 400 meters per second at the angle shown, so it's coming in an angle there. The mass of the bullet is 0.004 kilograms, a very small mass compared to that bar that it's striking, but it is coming in at 400 meters a second. The bullet strikes and embeds, so it becomes part of that, and the things whip up together. And then it says find the omega of the bullet and the bar after impact. And they're going to have the same omega because they're going to be part of the same bar at that point, right? They're all traveling together, so it's the same omega that they're talking about. So, well, let's go through it. Our free body diagram. I got my bar. All right. I got forces acting on this thing. I have reaction up here. Right here. OX and OY. I got mass times gravity acting in the center there. And then that's it, really, except for, just kind of show you this internal force pairs. There would be, right, like a kind of a reaction force from the bullet striking it, but then the bullet would also have it this way. That's what we mean by an internal force pair. The bullet striking the bar striking the bullet. So those two internal forces cancel each other out. Internal force pair cancels out. So that we're left with that. Okay. The second part says, let's look to see if linear momentum or angular momentum is conserved. Okay. In this case, what do you think? Is linear momentum going to be conserved? Is there any external forces acting on this thing? Two. These guys. Right? They're external, right? They're external, right? Those suckers affect what's happening in that bar right there. They're external. They're external reaction forces, right? They're being applied by the ground or whatever that bar is attached to. They're being supported there, and so because OX and OY exist, that linear momentum is not conserved, right? Another way to look at it, right, is if this, we're going to see in a minute, but that vertical component, right, that bullet, or even if you just, that bullet that came in and it's going to impose a downward thing right there. Well, it's not going to move, right? If that thing comes in, that bullet comes in and imposes a big downward force to it, well, it's attached to that. OY is just going to absorb it. It's not going to keep moving down. It's done. It's not moving anymore. That linear momentum is not conserved, okay? Or if you think about if the bullet struck up here, right, that force would just go right into that external force and just be canceled out. And so there is no linear momentum, or there is no conservation of linear momentum. Say some of the forces do not equal zero. Linear momentum not conserved. Okay. Does not equal zero, I should say. In this case, though, some of the moments, right? The sum of my moments equal to 0 around any point. Okay? Basically, one place. The sum of the moments right here are equal to 0. Right? That has no moment arm, that has no moment arm, that lines up with it, and then these guys are canceling each other out. So one place that the moments are equal to 0, and that's up here at O. Other than that, I cannot say angular momentum is conserved about this point right here, because it's not conserved about that point, because there is going to be a reaction moment that's happening around that point. Same thing here, right? So the only place is some of the moments about O. So in this case, we found a point O is equal to 0, so then angular momentum is conserved. And keep going about O. Okay, so now we're ready to kind of go down to part 2. I mean, this is all part of 2, so we'll just do 2 continued, and that's going to be to do angular momentum. Right, we said that they're conserved. So the equation for that, right in the equation here, HO, we'll call the bullet B1 plus HO, we'll call the bar is equal to HO B2 plus HO bar 2. There's our equation for conservation of angular momentum. Now, this guy's going to be, so that bar is at rest. So it's just sitting there before that bullet strikes it. And so it's not moving at the beginning. So that term right there, it goes to 0. The HO bar 1, it's not moving. So all the angular momentum is going to be in that bullet coming in. Okay? Very small mass, but traveling at a very fast speed. Yeah. Yeah, but then we just can't answer it. Yep. If we can't use something there to help solve it, we don't know what it's doing. Yeah. Try to think. If neither are conserved. Yeah, I mean, if we had an external, well, yeah, I mean, if that wasn't a pin support at the top and it was a fixed moment at the top, then neither of them are conserved. And then it gets weird. I don't think you could do it. It's like it's indeterminate, it's statically indeterminate. You got that guy coming in. You can't do it with energy. I think it just, who knows what the hell happens. Okay, and so one of those. So there we are, right there. So that guy HO bar 1 is equal to 0. Huh?
Why is it equal to 0?
Oh, because it's not moving. So the bar at the very beginning, it's like the bullet's coming in super fast. And then that bar is just hanging there. And so it has no, it would usually be IO times omega, but omega is 0. So that one's going to be 0. Good question. But the bullet, though, that's booking, right? That's coming in. And so we got to look to see which one we're going to use there. Do we do mass center? Do we do, what do we do for that one? And it's not really spinning. I mean, technically it is spinning, right? Because it has rifling. And so typically a bullet would have rifling, right? But it would be around a different axis. We're just doing 2D stuff. Let me see, go back to my HO equations here. Yep. All right, so that bullet's coming in. It actually is spinning around its own mass center, but kind of around a different axis. Kind of negligible for this side, right? Because the rifling gets it spinning. But really, I'm trying to figure out what the angular momentum is about one point, and the angular momentum about that one point is O up at the top, right? And so we're going to use this guy right here. It's going to be this equation that we're going to use. This is the angular momentum of the thing spinning about its own mass center, plus this other component, right? And that's the moment of linear momentum. That's the moment arm, and that's the linear momentum. So it's the moment of linear momentum. So we're going to ignore the fact that the bullet's rotating about its own axis and just do this RG as seen from O crossed with MVG, okay? When we talk about the angular momentum of the bar that's rotating, right? We're going to use this guy, IO times omega. That's the angular momentum of a bar, or just angular momentum of an object rotating about a fixed point. So when that bar starts rotating, it's going to be fixed. It's going to be rotating around that fixed point O. And so we're going to use that IO times omega. So let's go back down. right? Let's fill out this equation or fill it out in as best we can. HOB1, like I said, it's going to be R crossed MVG. So this is R bullet as seen from point O. That's the moment arm. Crossed with MVB1 is equal to, again, that same moment arm. RB is seen from O. Crossed with MVB2, how fast the bullet is going afterwards. Plus, now I have to add in the angular momentum of that bar that's rotating, which is going to be IO times omega bar. Okay. Okay, so that's all the components there. Okay, so now let's fill in. So it's R cross MV, that's the angular momentum before the impact. R cross MV plus IO omega bar is the angular momentum after the impact of the whole system. Okay, so let's fill in all the components here that we know. RB is seen from O. So this bullet, I got it drawn off to the left here. It'll be like when it's down here. This distance, 0.75, is like when it actually impacts it. So like, it's not at 0.75 and then a second later it's a little bit lower. It impacts it at that height is what I meant. Okay, so you can redraw that sucker like in the middle here if you want, right? So I need to figure out that moment arm. That moment arm is from here down to there, right? RB is seen from O, and so that's going to be negative 0.75 in the J direction. In the J direction, and I cross it with my mass is 0.004. That's the mass of the deal. And it's traveling at 400 meters per second, but then the direction is cosine 30 in the I minus sine 30 in the J. Right, because it's coming in at an angle right there. It's coming in at an angle, so it has an X component and a Y component. That angle there's 30, so that's what this is right here. 400's the magnitude, and then the cosine 30 and sine 30 are the direction in the two directions. Okay? That's all the left-hand side. That's equal to negative 0.75 in the J crossed with 0.004 times VB2. I don't know what that magnitude, I don't know what that is yet. Plus IO times omega bar in the K direction. This IO we haven't calculated yet. This will be ML squared all over 3, all over 3. Just figuring out I about the fixed point. This ends up being equal to 5/3. Okay, so there's our equation, right? That we have to solve it, because what I'm after is this omega bar. The problem statement says, what is omega after the collision? So I'm after this omega bar. And I know all this stuff. I know this, but I got two unknowns still. Or I'm sorry, I'm after this, but I got two unknowns. I got VB2 and omega bar. And so that's where kinematics come in. I have to tie them together. Yes, sir?
So for the angular momentum of the bullet, could you treat it like a point mass and just also do I omega for it?
Absolutely. So we're going to talk about that. So we're going to talk about it right now. So I'm treating it as separate, right? It's going to come in, it has mass, it's going to embed, and then it's going to swing up. And I'm keeping track of the velocity of that bullet and the velocity of that, the omega of that bar as being separate items. But I think what you're asking is, once it's embedded, can I come up with a new I that includes that bullet attached to it? And yes, you could absolutely do that. I could say, all right, now that the two are acting together and they're stuck together, I would have you use the parallel axis theorem and figure out, a new I that includes this guy and this guy. You'd have to calculate a new mass center, and then you could figure out what the I is about O as you went along. You absolutely could do that, right? And I think in your homework, there might be one of the problems where it's a little bit easier to do that, is you get a combined moment of inertia, and then this, if you got a combined moment of inertia, all you'd be left with was just this new I and omega bar, and you wouldn't have this other part. And you end up with the same exact answer as doing it this way. You can treat them separate, or you can combine that I, either one. And so in this case, I left them separate. So now I have to come back and relate how that guy moves compared to how that thing rotates. Okay, they're attached to each other, and so I could do that. I just do my kinematics. This is where kinematics come in. I think kinematics is step 3, I think. Okay, kinematics. All right, it's just going to be R times omega, but in case you don't see that, you could go like this. You could say, well, VB, VB2 is equal to go from a point that I know something about. I know the velocity at point O is 0, VO plus omega bar crossed with RB is seen from O. As VO is 0. And this is just omega bar in the K direction, and I cross that with negative 0.75 in the J direction, and then what I get is 0.75 omega bar in the I direction. All right. And so that's what VB2 is, so that's what goes right there. So if I plug that, I just came up with a relationship between omega bar, and again, it's just R times omega, right? But again, if you don't see that, you could do your kinematics from the start, and that's what you get, 0.75 omega bar in the I. Right? And then now, we can go down and we can solve it. Right? So I calced all the stuff up above. Like, these are all just numbers, so I just calculated that whole thing. Also note that, like, right, it's still just a moment, right? So if you consider this a force coming in, if this is just a force, right, only the horizontal component is causing a moment about that point, right? You remember that from statics, right? I mean, the vertical component, you know, when it's actually over here, right? That vertical component isn't causing a moment because there's no moment arm for that one, right? It's lined up right here. Versus only the horizontal component will do anything there. Same thing with this. This moment does the same thing. And how it takes that into consideration is with this cross product. It's 0.75 in the J crossed with this value. So a J crossed with an I gives us a K, but a J crossed with a J gives us a 0. And so that component goes away. So it's only the horizontal component. So when you leave it in the cross product thing, just like when you did R cross F back in statics, same thing happens here, right? If you wanted to, you could just ignore. You could have seen that. You could have seen, oh yeah, absolutely. This is, I see that this is coming at an angle, but really it's only the horizontal component that's going to cause that angular momentum. So I'm going to ignore the vertical component and only put in that component. You could do that, or you just put the whole thing in and let the cross product take that out. The J crosses J goes to 0. Okay. Anyways, I just wanted to point that out, that the cross product takes care of that for us. So all we're left with is the K direction. So this ends up being 1.03, and the K is equal to 0.75 times VB2. VB2 is just 0.75 times omega bar. That's where that came from, times the mass, the 0.004, all that times omega bar. So one of those 0.75s, 0.75 and omega bar, that's what VB2 is. And then this is the 0.75 that was there before, and then that's the mass. I just wanted to write it there with all the numbers out front in the K plus IO, which is 5/3 times omega bar. Okay. Good thing everything's in the K there, right? So that's it. We know everything in there except for omega bar, and we can solve. I do want to point this out right here, though. This is really small. Right? In fact, this ends up being 0.0023, which means this could probably be ignored. Right. Ends up being really small. 0.0023. That's compared 0.0023 compared to 5/3, right? So this is, because you'll add this on to 5/3, right? And so 2 2/3, is that what that is? 1 2/3. Yeah, anyways, this is really small. It's not going to make that big of a difference. So you could probably just ignore the effect of the bullet after it hit. Before it hits, absolutely makes a difference. Coming in at 400 meters a second, right? It's going to slam into that pretty fast. Once it's hit though and embedded, you could probably ignore it because it's just changing things just slightly. Or another way to look at it, if you were going to adjust the moment of inertia like we talked about, you got something that weighs 0.004 trying to affect something that weighs has 5 kilograms, right? So you have the whole bar is 5 kilograms. A little teeny bullet weighs 0.004 kilograms. It's embedded in it. Who gives a shit, right? We'll probably ignore it. Yeah.
If I did that on the exam, would I get marked out?
If you make the assumption, I go, that's probably really small. What I've done on an exam in the past is I say, neglect the bullet after the impact, right? And it makes your life a lot easier because if you neglect the bullet after impact, it just goes R cross MV into I O omega, right? You don't have to worry about tracking where the bullet's going after that. You get to ignore it. And you don't have to calculate the moment of inertia. So usually the exams in the past, I've said ignore that. If I don't say that, then you probably shouldn't ignore it unless you write a little note saying this is going to be small. I'm going to ignore it. Okay. There's some cases where it absolutely makes a difference. If this was a 2 kilogram bullet slamming into a 5 kilogram, that's a big bullet, but if a 2 kilogram bullet slamming into a 5 kilogram bar, then it makes a difference. Absolutely. But if it's really, really small, it probably doesn't make a difference. Yeah.
So we were only able to solve this because we saw the internal forces cancel out, so the moment is 0.
Yeah. The resultant moment for the system is equal to 0. It gets a little weird when we talk about systems, but really, there will be a force that's acting on that bullet, right? And then it's going to change how that bullet is moving, right? And then that bullet is going to impose a force onto that bar, and it's going to change the angular momentum of that bar, right? The bullet will change the angular momentum of the bar will change the angular momentum of the bullet, absolutely. But as a system, they cancel each other out. Yep. But they absolutely affect each other. And so these things are doing something, right? But they're doing the things to each other, right? That's doing one to the bullet's doing it to the bar, but as a system, they don't do anything to the overall angular momentum. Yeah.
I didn't see the question, but I was like, how do we know the bullet can go through? But it said
Embedded. Yep. If it goes through it, again, we're into the category of who knows. I don't know what happens at that point. There's some information that's missing. How much of its energy did it impose upon it as it passed through? Right. I don't know that. So that's a good question.
Would it be like if it went through it and say it came out and fell out with zero energy, would the problem be the same?
If it came out, you say if it went in and then. Yeah, I think it would. I think it would because it would be the same as if we ignored it after impact. Yeah. It helps to make those sound effects. Right. And so there's everything, right? You could probably ignore that bullet. The next problem we will ignore it. Let me just write down the answer here. The answer ends up being 0.623 radians per second. Right. If the problem, and that was it, that's all it asked is what the omega was after the impact. If the problem asked how high did the bar rotate after the impact, what would you do? Yeah, you do work energy, right? This is what its omega is. right after the impact, and you could take that and figure out how much it went up. All of that kinetic energy from that impact would then be transferred into potential energy, and you can figure out that height. So the next one we'll do. Any questions about that one? Oh yeah.
The hypothetical work energy section.
Yeah.
You would have to use, for the potential energy with the height, you'd have to use this mass center, correct?
Mass center. Yep. You'd use mass center. Yep. You'd figure out where the mass, when that thing whipped up, it would be where that mass center goes. It'd be the change in that mass center height as it swung up. Yep.
If we make the assumption to neglect the velocity component of the bullet there, will you have to include the mass of the bullet in your moment of inertia for the bar?
No, same deal. Is if you're saying that the bullet's mass is what the statement would say would be neglect the bullet after impact, and so then that would you wouldn't have to put it in this, right? Because you're just neglecting it. The mass it would be like ml squared over 12 m0, and so it wouldn't get transferred in there. So yeah, I would ignore it from this I, and I would ignore it from that over there. If you're doing it this way, then you don't put the bullet in that I, right? But if you put the bullet in that I, you get to ignore this part. And so if it just says neglect the bullet after impact, just leave it out of that I and don't put it in there. Yep. Okay. So here's this next one. We're not gonna do it today. We'll do it on Wednesday. But here's the same type of problem, but a little bit different. That there's a roller up at the top, and so that guy's coming in 1,000 meters a second. And this is gonna be one of those cases where linear momentum is conserved and angular momentum is conserved. Because if we look at our free body diagram, there's no forces in that direction and no. Anyways, it just turns out that angular momentum, and you have to use both of them to solve this. If you don't use both of them, then it's kind of unknown what's going to happen to it. So we'll do that one. We'll do that one on Wednesday. So I'm grading exams right now. I'm hoping to have them done just like we've been doing the last three. Have them done by or last two. Have them done by Wednesday. We'll go over them on Wednesday. So cool beans. That's all I got for you today. So I know letting you out 7 minutes early. But if you have any questions or anything, you can stick around and come. This would be a good time to come and ask me about stuff, and then. That's all I had.